Today we're going to be starting relative motion. We'll do that first. So, relative motion. And for our opening discussion on relative motion, I need to draw something really fast. We're going to talk about this from the standpoint of one-dimensional motion for just a few minutes, because it tends to be easier. What's interesting is that relative motion actually is the idea behind Einstein's relativity. If you take what we're going to talk about today to the extreme, things in the universe don't seem to work out like we thought they would, which is why there is a whole study in relativity. But relative motion is the way in which we add vectors together. That's really what it's about. It's about vector addition. And although we're going to be concentrating today on velocity vectors, every vector obeys these properties. So you can't add vectors together the same way you would add regular numbers together. Adding vectors together requires more care in dealing with direction. So although we're going to start with one-dimensional motion, which is relatively straightforward, I want to point out that the real goal today is to explain the difference between graphical solutions and mathematical solutions. In order to do the graphical solution part, you'll need a ruler. I would encourage you to have one available to you in the next few minutes. So, we're going to focus on velocity, which, interestingly enough, is something that you guys have a lot of experience at. So, we're going to say that you are in the back of the truck and that you have a friend who's standing in front of the truck, but off to the side, because the truck's going to be moving at 10 meters per second. So we don't want you to be hurt. Well, you won't be hurt. You're in the back of the truck. We don't want your friend to be hurt. Now, let's say that you are holding a ball in the back of the truck. Everybody okay? How fast is the ball traveling relative to you? Thinking zero. Is it changing its position relative to you? Velocity is changing position. So in this instance, the ball's relative velocity is zero because it's traveling in the truck. The truck is what's known as a reference frame. Since you are part of the truck, you are part of the truck's reference frame. So from your frame of reference, the ball has zero velocity. Interesting side note, humans can't detect velocity. Their bodies aren't made to detect velocity. You really have no idea whether you're moving or not. Your body detects when motion changes. That's what your body can detect. You have very sensitive acceleration detectors, mostly in the ears, which help you detect upright and such, but also your endocrine system is very much attached to this sensation, which is why sometimes it feels a little funny when you're on certain kinds of rides. Right, gentlemen? Gentlemen know this a little bit better than ladies, but having never been a lady, I really couldn't tell you. But having been a gentleman, they don't want to admit it to all of you, but yeah, it's true. Something around the no-no square area. And it's because our body's endocrine system has the ability to detect acceleration. But your body can't detect velocity, which is why it can be fooled into thinking it's moving when it's not. All of you have probably caught motion outside the peripheral of your vision and thought you were moving for a minute. The word tends to be vertigo. When you catch some motion, that makes you think you're moving even though you're not. But also, many people think, like when they're in a plane, that the fastest part of the plane is takeoff and landing, which is not even close. That's the slowest part of the time that you're on a plane. But it feels like you're moving fast because all the stuff outside of you is close and you can see it moving rather quickly. But that's only about 150 miles an hour. When you're up at cruising altitude, you're probably more likely to be traveling about 500, 550 miles an hour. But you can't tell. All your points of reference are gone. You're in a closed box. And even if you look out the windows, all the things are far away. Velocity isn't something you can detect without having other clues. Visual clues help, but you can be fooled. That's why all those rides that close you in and give you a view screen to look at, You think you're moving, you have no other reason not to believe that, except that it's a ride. And you probably know you're not, you know, in a rocket or something like that. So, in this instance, the person, the friend, how fast do they see the ball traveling? 10 meters per second. Simple, right? Now, if you throw the ball forwards at 5 meters per second to your friend, how fast does your friend see the ball?
15.
Got to be 15. The ball's already moving at 10 meters per second relative to your friend before you throw it. You throw it, giving the ball an additional 5 meters per second. If we were to take the velocity of the truck and add it to the velocity of the ball, we would get what's called the resultant velocity. Now, in one dimension, this is pathetically simple, but I still need to take a moment for us to talk about it. So, when adding vectors, graphically, we add them tip to tail. So I would take the first vector, 10 meters per second, and draw it first. I'm drawing it to the right, because that's the direction the truck's moving. The next vector is the velocity of the ball. I'm going to draw it half the length, because the length of a vector represents its magnitude, or its size, or the scalar portion. Now, I don't want to say that 20 times. You guys don't write anything down that I say. You only write it down if I write it on the screen, but I'm not writing all that down. The length of a vector is its magnitude. When doing this graphically, there should be a reasonable attempt to preserve length, because it's the magnitude, it's the size. It is the scalar portion of the vector. So, adding two vectors together, and you can add as many as you want, but we're only adding two together. The resultant is a vector that is drawn from the starting point of the first vector to the end of the last vector. So the resultant that starts where the first vector started and ends where the last vector's tip is. The top two vectors are called component vectors. They're being added together to produce the resultant. The resultant is the sum of the two vectors. Go ahead, Kyle.
I have a question. So when you throw the ball and it's going 5 meters a second, isn't the truck moving faster than the ball?
Yeah.
So wouldn't the ball be moving 5 meters a second?
Nope.
It's just confusing me because the catch would cut.
I believe it's confusing you. But the ball's already moving 10 meters per second relative to the person on the ground.
Okay.
The person in the truck is adding an additional 5 meters per second to that. It leaves the front of the truck moving 5 meters per second. Now, your experience with this might be different, because if you've ever thrown anything out of the back of the truck, you know that there's wind acting here. And the wind might play a role in this. But we're assuming right now that we can ignore that, just for demonstrative purposes. Now, you could just as easily wait till you pass your friend, in which case you could try and turn around and throw the ball to them after the truck has passed. Unfortunately, for your friend, they probably still wouldn't be able to catch it, would they? Because if we look at what happens here, this would be what would happen if we said the velocity of the truck minus the velocity of the ball. Putting the minus in front of a vector flips its direction 180 degrees. And although I don't use minuses in the vectors very often, vector addition and vector subtraction are something you're supposed to know. So if I tell you you're going to subtract a vector, you're going to take the vector and reverse its direction. And then add the two vectors together. That's what the minus sign indicates. And this will produce a new resultant. So under this circumstance, I'd have the 10 meters per second representing the truck, and then the 5 meters per second representing the ball. The result is that the ball is still moving forwards at 5 meters per second. That is the resultant velocity of the ball. The ball wasn't thrown fast enough to compensate for the fact that the truck is moving forwards. this is one-dimensional motion, which we're not going to spend hardly any time on one-dimensional motion like this. That's what we've been doing for the last couple of weeks. We've picked direction, and our vectors have been either moving forwards, positive, or backwards, negative, or up, positive, and downwards, negative. But is what happens when we have, say, a river, and the river's flowing this way at 3 meters per second, and you wish to swim across the river that way at 5 meters per second. This is also adding vectors. This is more in line with what I would like you to be able to do. I think we all know that you are not going to make it here. Are you? No. Well, not the way you're aimed. If you aim across the river and the river is moving, I mean, this is Florida. We've all seen a river, I hope, or been near the water. It is Florida. So I would hope you've been near the water. And this is the idiot that tries to swim from Honeymoon Island to Caladesi. Tide's flowing. They're not necessarily going to make it. You see those morons all the time. From the comfort of Caladesi, of course. You're going to probably travel that way. Even though you're not facing that way, you are facing straight across the river, there are 2 vectors here. There is your vector, which if you have a ruler, you should draw straight up on your paper, 5 centimeters long. That's the goal of using the ruler here, is the ability to do this graphically. I don't have a ruler, so I can't make sure mine is perfectly 5 centimeters. But this is your swimming velocity. But I want to add to it the current of the river. Now, to add 2 vectors graphically, I add the next vector starting from the tip of the first vector, aimed in the direction that the vector is heading, and sizing it the appropriate size. So you should draw it at a right angle, which should be easy to do with the lines on your paper and such, and you should make it 3 centimeters long. You now have a scale where every centimeter on your paper is 1 meter per second. And using the blue lines and careful precision, you can make them at a right angle to each other. This is velocity of the swimmer plus velocity of the current will equal the velocity of the result. The answer is not going to be 8. The person's not traveling at 8 meters per second, even though one of them is 5 and one of them is 3, because the person moves along this line. The resultant is drawn from the starting of the first vector to the ending of the last vector. That is the resultant. So now that we have a resultant vector, we should be able to figure out the angle they make as they swim across the river and their actual velocity. This is the velocity relative to a non-moving spectator on the ground. This would be the ground speed of the airplane. This is quite literally the ground speed of the swimmer. Now, if done correctly, a protractor and a ruler can tell you this answer, because you have access to both, which is why I would recommend you have these to try it out. The measured length will be very close to the right answer. So if you measure it and get your answer in centimeters, that's probably the number of meters per second. On the other hand, you know that I'm going to make you do this the other way too, right? So at this point, you should be able to figure out for me how fast they're swimming and in what direction. I'm going to give you about 60 seconds to work that out, either using a protractor and a ruler or using your calculator. You really don't care which. They're both going to be very close to the right answer. Assuming you know how to use a protractor. I've had students who are not protractor savvy. 60 seconds, and then I'm picking one. We have to hurry because the bell rings. degrees? Anybody agree with 35 degrees? Did you measure with the protractor or did you calculate it? Okay. I think it comes out to be like 31. Is that right? If you calculate it on 31, I would buy 35 from a protractor. So believe it or not, these two, if you get it from a protractor like that, you're a couple degrees off. All right. You figure out how fast they were going?
It's like 5.8.
Yeah, so we'll say 6 meters per second for now. Now, here's our problem. How do we express what this person is doing? Their ground speed, their speed relative to where the guy on the shore is standing. We can say they're traveling at 6 meters per second at an angle of 31 degrees, but that doesn't really mean very much. If I tell you they're traveling at an angle of 31 degrees, that really doesn't tell you anything about how they're moving. And worse off, you're being trained poorly to deal with this kind of problem. If you don't believe me, who has already finished dealing with unit circles for a year? Who are the folks who did unit circles last year? Fun times, weren't they? Wasn't that good stuff? You had to carry that ridiculous thing in your backpack or in your binder that you can open up that had all the unit circle angles on it, refer to it all the time, carry it with you at all moments. Do you remember all that?
Yes.
Here's the reason that's going to be a bit of a problem for us. And there's a number of reasons why. One of them is because you think x and cosine go together and y and sine go together. That's not true. That's wonderful for that class, but that's not true anywhere else in life, or especially in this class. And let me tell you something else that's a problem. And you guys who haven't done the unit circle yet this year, I feel bad for you, because you're going to have my class, which is going to do it one way, and you're going to have that class, which is going to do it not the right way, but the math way. Math likes consistency. They like to set a standard. And so, this is their standard, right? This is what you learned in their class. Those are all the angles. Maybe it goes back around and it's 360 over here. And then if you had this last year at the unit circle, you know that you've got pi over 2 and pi and 3/2 pi and 2 pi, right? Sound familiar? Yeah, well, here's the problem. Could you guys point north? We're in my classroom, we're on the earth. Which direction is north? This is always fun for me. It's less fun for you. So clearly some of you know and some of you don't know, or some of you think you know. Yeah, north is this way. So
Wait, north relative to me or north relative to the earth?
that would be the same thing. North is only one way. It's not like you are the center of the world. I know you might believe that, but that's not exactly what's happening. North is this way. And well, let's make sure we know them all then. If north is this way, what direction is west?
Never ever smoke weed.
What?
What did you just say?
Never ever smoke weed. Yeah, but that goes the other direction.
Never eat. I was taught never ever smoke weed.
We can all have our own mnemonic. So south
We
is
just passed from 6th grade.
south is that way. East is good. That was scary. North, south, west, east. If I was to draw them, would you draw them this way too? Folks, I would pay attention real quick, because here's your problem. Actually, it's not your problem. You didn't make up this problem, but it's going to be a problem. Because we think of north as 0 degrees. And we think of, you could just say, well, can't we just turn it and make north where I put the E? Because wouldn't that be 0 degrees then? That sounds great until you realize east is 90 degrees on a compass. And south is 180 degrees, and west is 270 degrees. So if we go by compass instructions, like Google Maps gives you, not only is it different than your math class, it goes in the other direction. Sorry. But math is telling you one way. They have their standard way, and then the rest of the world, when it comes to like what direction things are, has another way. That's going to be a problem for you. It's really not a problem for me, but it's going to be a problem for you. Because how now do I ask what angle the person is swimming?
Northeast.
That 31 degrees isn't even related to the math direction. Right? Math would have been, based on the way this picture is, math would have an arrow this way, and this would be the x direction, and we got the wrong angle. Yeah, I know you can figure out the other one. But how does this guy who's sitting right here know what we're talking about when we say 31 degrees? Or how do I communicate it to somebody who's not here that the guy is swimming at 31 degrees? Well, relative to what? You have to provide relative directions. You have to provide reference. I mean, you could say that the guy standing on the river says, facing directly across the river, he is 31 degrees to my right. That would be okay. That would be reference. You are telling the person who's observing where 0 degrees is, so that you can know how to measure the 31 degrees. For this class, most of what I'm going to ask you to do is going to be relative to north, south, east, and west. If it comes to something like this, where we're talking about a person moving through an environment, we'll establish what direction is north, and then you make your directions relative to north. We don't do this very much. A lot of our angles are things like it's 30 degrees from the floor. So understand that you have to provide reference. Now, there are a couple of standard things I want when it comes to providing reference. And it's not particularly hard, but let's get these things out of the way because they're just in the way. And go back to our little problem here. So when I'm looking at this problem here, I would say that the guy is swimming at 6 meters per second. That part's easy. You can all agree how fast he's swimming. I want to put a little division symbol here, something that kind of looks like you're dividing, but it's upside down. It separates the size of the vector from the direction of the vector. This is where the angle is going to go, 31 degrees. But now you have to provide reference. You have to tell me what you're going to use as 0 and how you're measuring your 31 degrees. For me, I'm going to say if this way is north, then it's 31 degrees east of north. Because I'm telling you, to face north and turn towards the east, 31 degrees. So I am 31 degrees east of facing north. That's what this means. Go ahead.
You can't just say northeast.
No, because northeast can mean either one of these angles,
Oh, okay.
right?
Yeah.
So unless it's 45 degrees, we have to tell them which side it's on. By the way, be really careful about assigning x and cosine and y and sine together. That will never work in this class consistently. It would not work here. Meaning if I told you that they were moving at 6 meters per second at an angle of 31 degrees, and you just assumed that x always went with cosine and y always went with sine, you will get the values for the 5 and the 3 way screwed up. So you have to consider the triangle that you're working with. Let's practice. I think practice is. How about we'll do an airplane. Airplane is traveling this way. And we'll make it going really fast, like 250 meters per second. So here's my airplane. Whee! Airplane. And we're going to say the wind is this way. And this is the wind. And let's go with, let's go 100 meters per second. So this is like 200 mile an hour winds. Our plane's going like 500 miles an hour. So very unrealistic. This would like destroy the plane, rip it in half. But it also makes for a nice big triangle. So it's easy to do the work on it. I would like you to tell me the actual ground speed of the plane, which would be the speed and direction of the plane relative to the ground. Let's make the assumption that the plane is traveling due west and the wind is due south. So I want the actual velocity of the plane relative to north, south, east, and west. Now, I'm going to walk this through a little bit. First, there is an implied triangle here. Doesn't look like it, but it's implied. Remember, we add our vectors together, tip to tail. So I'm going to start and say that the plane's velocity is the first one. That's the first vector. Then I'm going to add to it the wind's velocity. So that the actual resultant velocity is along that line. You have to create the triangle. It's not going to necessarily be there for you. So I took the wind and merely moved it down so it was easy to see. So put the wind there. Remember, they go tip to tail. Then I draw my result from the very first vector all the way to the end of the last vector. That white line is the resultant. So I'm looking for this angle and this length. The angle and length part, that's the whole trig portion. Just got to get that number and that angle right. Last class period, I had some lack of success on doing this one, so I'm going to give 60 seconds. Here we go. Christian, give me one of the numbers.
R I found
270. Okay, so 270 meters per second. And Abby, can you give me theta?
Uh, 22.
22. Victoria, do you agree? 22.
I haven't gotten it.
Lauren, do you agree? 22.
Also haven't gotten it yet.
Okay. Anybody agree that it's 22? Okay. 22. Now, let's just for argument's sake that you didn't know how to do that, the 100 squared plus the 250 squared probably would give us the 270. And then based on that angle, this is the opposite side, this is the adjacent side. So opposite 100 divided by adjacent 250 is going to equal tan theta. No, I'm dropping some steps here, but that's because I'm hoping that we can move past that. And then take the inverse tan of both sides, and that gives us our 22 degrees. Just doing that just to make sure that we're all on the same page here. All right, so that gives us the information, but that's not quite the answer. To express the answer, the ground speed of the plane, I would say the plane is traveling at 270 meters per second. And then I'd have to provide reference, 22 degrees. Well, that 22 degrees looks like it starts facing west and then turns towards the south. So I am 22 degrees south of west. Yep.
How do you know which one to put first, like west or south?
Well, I'm hoping the word of is helping here. But again, I start facing west, I turn towards the south, so I am now south of west. I'm trying to use language. Does that make sense?
Yeah.
Is that all right with everybody? I mean, you're welcome to explain it more thoroughly than that. You can say face the west and turn towards the south, 22 degrees. If you're confused about this, I use shorthand here to make it faster, but you don't have to. You can explicitly state what you're doing, and that'll be fine. Maybe another practice. Now, I'm being kind right now. Kind is the wrong word to use here, but I'm being straightforward. You'll notice I gave the wind due south, the plane traveling due west. That's not reality. Reality is going to have to be that I can add any two vectors together in any direction, which will be harder. Right now, I'm just trying to cover some basics. So I'm going to give another basic, but then we're going to have to probably come to grips with the fact that they're not going to be like this. Real life is a little bit more, messy. So let's say a boat. Sure, that's a boat. This way at 10 meters per second east. And the current this way at 4 meters per second add the vectors tip to tail. So I can either add the water to the boat, or I could add, maybe not, maybe not. Come on, my friend. There, I could add the boat to the water. Your answer will be the same. So, which one did you guys do? Did you add the water to the boat or the boat to the water? So you did like this?
Yeah.
Okay, I could do it like this too, but you'll get the same answer. Now, the angle will be different, a little bit. You'll get the complementary angle, right? The one that's 90 degrees minus that one, that's a complementary angle. So it doesn't matter which one you choose. And we'll prove that in just a minute. But here's this is what it sounds like you guys did. And you're finding this angle. So we're about done, I hope. Luca, can you give me the resultant vector size?
Vector size would be
11 meters per second? All right, sounds good to me. And I don't know who to call in next. Nicole, can you give me the angle? Okay, I'll be patient.
I
22 degrees again? Okay. Everybody else get 22 degrees? All right. Now, if I was to express this, I'm thinking 11 meters per second, 22 degrees, and that looks like I'm starting by facing east and turning towards the north, so I am north of east. Now, I want you to follow this real quick. Move this, put this right down here. And just see if I can take this piece and move it right over there. Little arrowheads. Like that. There we go. So I want to point out, it doesn't matter whether I do the water first or I do the boat first. You'll notice the result is the same size. You guys see that? The difference is I'm going to get a different angle for sure, because now I'm dealing with this angle. Could you do me a favor real quick and find that angle? It's just going to be 10 over 4 instead of 4 over 10. 68 degrees. Now, this angle and this angle are just complementary. You add them together, you get 90. Now, the answer is slightly different though. This is 11 meters per second, 68 degrees east of north. Because I start at the north and I turn towards the east, 68 degrees. Yes, ma'am?
Could you have put the water on the other side, but like on the down? Does that make sense?
The other side on the down.
Like on the east side, and then below that line, and then did the angle the other way?
No. And like that?
No, like it's still from the water to the boat, but it's the other direction, so then it would be east of south.
I'm not sure what you mean, but let me see if I can kind of configure it the way you're talking. So that, like, looking like that?
It would be an angle going up to that, from the blue line to the yellow line. Like that, yeah.
No. And the reason why is, first, this isn't actually what the boat does. Does the boat actually travel along that white line? Now the wind is, or the current's pushing the boat upwards relative to the board right now.
Mm-hmm.
This would suggest that the boat travels along this path that's downwards. And the reason it doesn't work is simply because we have to add the vectors in a fashion that puts them tip to tail like this, or else your angles will work out wrong. The most common mistake students will make is actually this one. They'll start them both from here. And then they get, something even weirder. What angle do you even solve for here? But students do this all the time. So I want to be really, really clear that you have to add the vectors tip to tail. The order doesn't matter, but you still have to do it in this way. Now, I think before we get any more complicated, we need another one. It feels that way. So I was only planning on doing 2 examples, but I think a 3rd example is really, really going to be necessary here. So let's try it one more time. And let's just do, a boat again. Going downwards as the boat. 20 meters per second, south. And let's do the current is, I'll make it big enough where we get something here. So let's go with 10 meters per second to the west. I think we need one more practice. 22 meters per second. And angle of like 27 degrees. And I'm thinking, based on what I would have done with 27 degrees, that would be west of south.
It's the same question. How do you know which angle to solve for? Yeah. Because I got everything right. I just used the other.
If everything's right here except yours is yours.
63. It's yes.
Did you say 63 degrees south of west?
Yeah.
It makes a difference.
Yeah.
So neither one of these is different. They are the same.
Oh, okay.
So if you did either of those 2, you're fine. But if you did 63 degrees west of south, that would not be okay.
Okay. How do you draw the triangle? How would you?
I can draw the triangle, but
Okay, I got that right on.
can you draw the triangle?
I
I would draw the triangle like this, and therefore I would put the resultant vector like this, because the resultant starts from the first vector, ends at the last vector, and this angle is the result of doing tangent of 10 over 20, opposite over adjacent, which is what's going to give you the 27 degrees. And this tells me to start at the south and turn towards the west, 27 degrees. Kyle?
Should I be rounding for the nearest whole number?
Yeah, I don't care about that.
Okay.
We all right there? Kind of. Look, you don't have to write it west of south. You can say stand south and turn towards the west, 27 degrees. The boat is facing south right now. And this whole thing has to be turned this way, 27 degrees. So you have to find a way to communicate your point of reference and how many degrees from your point of reference. West of south is shorthand, it's quick, but if it doesn't work for you, be more explicit. It's better to say exactly what you want, write a few more words, than to mess that up for something silly. Now, the truth is this is not at the level I would like you guys at. What I would really prefer to see, to do vectors that are already perpendicular to each other. This, like this. The second, something like, plane traveling at 250 meters per second south. And and maybe the wind
Too strong.
Do what?
30 degrees north of east at 100 meters per second.
It's the opposite of the two.
Yeah, it's an acute.
Now,
So right triangle.
look, you don't have the skill set to do this right now.
So
I want to be very clear. This is going to require more work. You have only this example right here requires more understanding. But this is the level I would like you to work at. You can't solve this using the method we just used. You have to do something else to it first. And part of the reason is, although this vector is fine, it's due south, this vector is not. We can only add vectors together if they are in the same direction or perpendicular to each other. That's what you guys have seen here. This one that's not requires more work first, ahead of time. Now, I'd like to show you how to do that, but we're going to run out of time today, which means that the vector work's going to take an extra day. We're going to have to do this on Monday. But this is, I don't want to spend more time on it. It's really not super critical, but I need to be able to work the vectors out. So I'm going to post practice. It is 6 pieces of practice. The first 3 are like this. Like the 3 are like this.
So if you set the triangle,
Okay?
if you set the triangle for that, would it be like this? It's like straight.
If I set the triangle for this one,
Wouldn't the other angle be 60 degrees?
But like it says.
I don't know what you mean by the other angle.
Like the angle right next to 30 degrees. Like,
A lot of people talking, so I can't answer everybody. This is what the triangle would look like when I put them together. And the result would be the white one. That would be the result.
is that a right angle or do you not know that?
It's not a right angle.
What?
It's not necessarily a right angle. That's why we can't do it that way. We have to do something else. Okay, have a nice